Good afternoon, good morning and good evening to all of you from wherever in the world you connected to the first day, the online day of the Science and Technology 2025 conference. I'm Monica Christa, Atmospheric Sciences Officer at the International Data Center of CTBTO.
And this is Mario Zampolli speaking, Hydroacoustic Engineer in the International Monitoring System Division at CTBTO. Together with Monica, we will be moderating this online keynote session, where we will see recent research results about two very large earthquakes which have struck the world this year. The first one is the Myanmar earthquake from the 26th of March, and the second one struck Kamchatka little less than 1 month ago on 29th of July. We will see very recent research results about both of these events from eminent experts. So please note that you can also submit questions to the authors via the online platform, and then Monica and I will relay those questions to the authors. So please.
The first keynote, the very first presentation of SNT 2025 is on the Myanmar earthquake and will be presented by Ch1 Wei from the Nanyang Technological University in Singapore. Ch1, the floor is yours.
Thank you, Monica. Now I'm going to share my screen. Okay, so thank you for the invitation from SNT 2025. And also thank you for the chairmen for the introduction. My name is Ch1 Wei. I'm an associate professor from Nanyang Technological University, also a visiting professor in Institute of Geology and Geophysics, Chinese Academy of Sciences. So the presentation title of my talk is The Supershare Rupture and Its Interpretation for the 2025 Mandalay, Myanmar earthquake. So this is a teamwork that have contributions from my current and formal PhD students and postdocs mostly, and some other collaborators from different parts of the world, as you can see from these logos. I appreciate their hard work and contributions to make this study possible. I would like to start my presentation from this picture or photo, which is summarizing a high-rise building in Bangkok that collapsed completely. This is a building under construction in Bangkok, which is located about 1,000 kilometers away from the epicenter of the Myanmar earthquake. Besides this complete collapsing of this tall building, the buildings in Chengdu, like the resonance, you can see the contrast between the shaking at the third floor and the 48th floor. Their amplitudes differ by a factor of 10, so that the top of the building sway much stronger than that from the other side, from the bottom. So this is a photo video taken in Bangkok as well. So not only this building that completely collapsed, but also other tall buildings experience pretty strong shaking or the resonance response at the top of the building. So this earthquake is pretty much a warning message for places like in Singapore or other places that are considered to be far away from active faults. This long period seismic wave can actually be amplified because of the resonance frequency of the building is consistent with the strong shaking period in the first floor in the ground. So my presentation is organized in this way that first I will introduce the plate tectonics and the seismic hazard in Myanmar, and then I'm going to introduce the data set that we use to constrain the kinematic rupture process, the surface rupture of the earthquake, and then going to follow by a very brief interpretation on the supershare rupture of the event. So Myanmar is a place that is known to have a high level of seismic hazard. The population of the country is about 55 million, and a major plate boundary type of stretch slip fault, which is the Sagan fault, as you can see from the top. this red dot here from 1946 all the way to the earthquake over there, all the way to the ocean. This is a very long strike slip fault that run through multiple population centers like Yangon City, Bago City, Mandalay City, and their new capital, Mandalay. The highway, the infrastructure, some of the infrastructure are shown here as this highway or railways that are connecting multiple major economic and political centers in the country. This is the way the highways maps that you can see that is pretty much overlapping. A lot of them are overlapping with the Sagan fault, which is the fault that hosted this recent earthquake. As briefly introduced earlier, that this earthquake is started from the northern portion of the Sagan fault. Its epicenter is indicated by this red star, and this heavy red line indicates the surface rupture produced by this magnitude 7.8 or 7.7 earthquake. And the slip rate of this fault, as shown in the lower left panel figure, is slipping or loaded in a rate of about 2 to 2.3 or 2.5 centimeters per year. And corresponding to its very long surface rupture, which is more than 470 kilometers in length, it produced intense ground shaking along its rupture, as shown by this intensity map provided by USGS. If we look into the focal mechanism, which are indicating by these beach balls, so each of these beach ball is representing an earthquake that occurred in the past. The size of the beach ball is proportional to the magnitude of these earthquakes, and they're color-coded by their depth. So when they're red, it means they're shallow, mostly in the crust. When they are blue, it means their depths are down to the in as deep as more than 100 kilometers. From this focal mechanism catalog, those beach balls are indicating the style of the focal mechanism of the earthquake, right? If they looks like this, means they're a strike slip earthquake, and the recent earthquake is this kind of focal mechanism. If you just look into this focal mechanism distribution, which is composed of near 500 events, it's combined from multiple sources, including those derived from my former PhD student, Wada. You can clearly see a gap along the Sagan fault, which is from Mandalay to Naypyidaw. Because this earthquake catalog is only available since about 1970s, so it means that this part of the Sagan fault has been relatively quiet until this recent earthquake. So this kind of quiescence between the big earthquakes is considered to be a seismic gap. And based on paleoseismological investigation, we know that it has been almost 200 years since the previous big earthquake that took place along this segment of the Sagan fault. So we had a lot of concerns about its future big earthquakes before this recent Myanmar event. So that was back to about 10 years ago when I started my faculty position in Nanyang Technological University. We realized that this is a place that are close to the next big earthquake. So so this is the seismic gap. So my research team, we actually deploy about 30 broadband seismic stations mostly along this gap, the seismic gap, as indicated by these orange colors. And the other organizations also are very interested in the seismic and plate tectonics in the country, so they also deploy quite a few broadband seismometers in the country. But those orange triangles are the stations deployed from Singapore, from my research team. So they were deployed exactly along the seismic gap, which is, as I said earlier, known from the paleoseismological investigations. So here also a big thank you to the technical office in Earth Observatory of Singapore under NTU. They have worked really hard to make this seismic monitoring possible. Although it's a bit unfortunately that these strong motion and broadband stations were taken back to Singapore because of unstable political and safety conditions in the country. So these instruments didn't record the big earthquake, the recent big earthquake, but they did record some events from teleseismic and regional distance since 2015. So these instruments were working from 2015 to 2024. And some of this data will be used, as I'm going to show you later. Besides these kind of possible near-field data and these global and regional seismometers, an important data set that we use to study the rupture process and surface rupture of the earthquake is based on space geodetic observations. This kind of technique has very high spatial resolution. One of these techniques is termed INSAR, interferometry of SAR images, which means that you use this kind of satellite scan through this area, and then after the earthquake, this satellite scan the same area, look into the difference between these two sets of images, then detailed surface rupture and deformation from the earthquake can be imaged. So this is based on SAR image. Another technique is called the cross-correlation of technique, which is which can be applied to the SAR images as well as optical images. The idea is kind of similar. You take a picture from the same place of the world and then come back again and do this so-called cross-correlation of their pixels so that they can, the advantage of this pixel offset tracking is that they would not saturate because of the very big surface deformation from the earthquake. So we can resolve not only the far field deformation produced by the earthquake, but also very near fault surface deformations, as I'm going to show you in the following slides. So the left figures is a collection of the geodetic data processing results. We use MAI, pixel offset tracking, and interferometries of these SAR and optical images to obtain. Here we have 14 images derived from the ascending and descending SAR images, as well as these different techniques. So I wasn't going to go through this in detail because this is a little bit related to these techniques. But the figure to the right is more intuitive. This is a three-dimensional surface deformation map produced by the earthquake. So the big map is showing the north-south deformation. So you can clearly see opposite north-south direction motion across the fault, which is very clearly shown in this north-south image. And this is to zoom in to the northern portion and to the southern portion. Because this is a near pure strike slip earthquake, so its north-south component is dominating the surface deformation. So in east-west component and up and down or vertical component, we see almost negligible surface deformation compared with the north-south components. With this kind of high resolution or high spatial resolution images or 3D surface deformation, we can precisely map the length of the surface rupture, which is more than 470 kilometers. There are some contrasts between the surface deformation to the north and those to the south. For the northern part, this volcano, or we call it single basalt, which was created by a basaltic volcanic processes. There is a pretty sharp termination to its northern end. In contrast to that, the southern part of its rupture terminates more gradually. And actually, the southern part of rupture is overlapping with the 1929 and 1930 magnitude 7+ earthquake that occur along the Sagan Fault. With the 3D surface deformation, we conducted a geodetic or static slip model for the earthquake. We use 9 fault segments. Segment number 1 is from the north. The epicenter is located on segment number 3. This is the depth wheel of this static slip model with maximum slip amplitude up to about 5.5 centimeters. There's this BZ diagram to the left is showing the resolution or uncertainty that we can constrain the dip angle and the dip angle of these 9 fault segments. The uncertainty, which is indicating by the yellow to red zones on this heat map, is pretty small. As you can see, it's ranging from 2 to 3 or 4 degrees in dip angle. Its dip angle is pretty vertical. It's near vertical, but there is an anti-dipping phenomenon or anti-dipping result, as you can see a bit from between segment number 4 and number 5. For the segments 1 to segment 4, they are near vertical or dipping to the east. But for those segments from number 5 to number 9, they are near vertical or dipping to the west. And this is the corresponding data, which is the top 3 panels shown here. And this is the model predictions from this slip model and this fault geometry based on this fault geometry. And you can see very high similarity between the data and the model prediction, which indicates a pretty well prediction or constraint from the slip model to the slip model as well as the fault geometry. This anti-dipping phenomenon is also supported by other evidence. So we have different observations. For example, this is this panel B is showing the dip direction and dip angle from the geodetic modeling. So with GNSS observations or GPS observations across the fault, these past publications are showing these when these green zones are located to the right-hand side, means the fault is dipping to the east. And this is another GPS profile showing that the fault to the south is dipping to the west. And these blue lines here are indicating the dip angle from the geodetic inversion, which is shown in the previous slide. And the middle panel C here is showing the dip angle from the focal mechanism or the bitch balls. So these are the bitch balls that when we assume that these north-south oriented fault plan, it's rupture fault plan, then its focal mechanism is indicating that to the north of the epicenter, the fault is dipping to the east and is almost vertical in the middle and then dipping to the west. So this is an important geometrical feature of this fault because as I'm going to show you later in the other velocity model and fault zone structure constraints, these faults indeed for the southern portion has to be dipping to the west rather than dipping to the east to explain the other observations that we have. So this is another wheel of this static slip model. This is a single basalt, as you can see in the previous image, that is located to the north of the epicenter. So the 0 location is the location of the epicenter. And these slip contours are the slip model from this 2012 magnitude 6.9 earthquake. Is located exactly beneath the single basalt. And this is also the northern termination of the 2025 rupture. So you can see that there's almost no slip when it ruptures to single basalt. One of the important reasons is because this 2012 earthquake has released most of the stress or strain concentration on the fault. It creates like a stress barrier that stops the northward rupture of the event abruptly. For the rupture to the south, as you can see, this slip amplitude is relatively small near the epicenter. This is likely related to the partial creeping on this fault segment. And those rupture to the south has slip amplitude between 3 to 4 meters, and it shows some kind of small wavelength fluctuation. And this in 1929 and the 1920-30 event, they were partially overlapping with the coseismic rupture of the recent earthquake. The panel to the lower shows the cumulative slip as a function of depth along different fault segments. This is fault segment number 1, and this is fault segment number 9, arranged from north to the south. And those numbers indicated here is the so-called shallow slip deficit, which means that the shallower, if this number is big, it means that the shallower portion of the rupture has smaller slip amplitude than those between the depth of 3 to 7 or 8 kilometers. Along this segment, which is the segment that has relatively small slip amplitude, the shallow slip deficit is also relatively large. And the GPS observation shows that this part of the fault is likely to be partially creeping. Its locking percentage is lower than those to the north and to the south. This is what you have seen earlier is the static slip distribution, what is dislocated on the fault. And what I'm going to show you now in the following slides involves more temporal evolution of the earthquake. But before we can do this temporal evolution analysis, I would like to emphasize that the epicenter location reported from USGS or NEIC is not that accurate. The red star here indicates the original. I'm not sure whether USGS has updated their epicenter, but this is their original epicenter. Using regional broadband stations and a calibration earthquake, we relocate the epicenter, or epicenter means the initial position of the rupture. Its total length is near 500 kilometers, but it starts from a point on the fault. And this beginning part of the rupture, it's a crucial parameter because the rupture speed of the earthquake would need a more reliable epicenter location. So by using this regional travel time information data from the earthquake, the main shock, and a calibration event, we relocate its epicenter to the blue star, which is about 30 kilometers, or actually more than 30 kilometers away to the south of the USGS epicenter. So with this refined epicenter, we have conducted several seismological analysis to constrain its temporal rupture process. The panel to the left is the back projection result indicated by these diamonds and squares. These are the back projection, or we can consider it to be the high frequency radiator from the earthquake. The size of these squares and diamonds are proportional to the intensity of the high frequency energy release along the fault, and their color are indicating their relatively timing to the epicenter origin time. So the blue means that the time is relatively close to the epicenter, which is closer to the red star, which is our refined epicenter. And as you move further to the south, this color indicates the timing of this high frequency radiator, or we consider to be the rupture front of the earthquake. It's located much further to the south. And these pitch balls are a kind of similar analysis. We call it the multiple point source inversion technique, which is using the regional and the global seismic observations to constrain the long period energy release as a function of time. These pitch balls are also color-coded by the same time color bar, which is the rupture time of these events. So with this back projection result in multiple point source, we can draw some lines across the pitch balls and these diamonds and squares because we know the time and location of these seismic energy release along the fault. So by defining the zero as the epicenter location along the fault, so this is the distance along the fault, and this is the time. By this kind of diagram, we can determine the rupture speed of this earthquake, which is about 3.3 kilometers from the epicenter to the south, to about 100 kilometers to the south. Started from about 100 kilometers further to the south, the rupture speed becomes about 5 or 5.5 kilometers per second. So this kind of rupture speed is already faster than the shear wave speed within the upper crust. So this kind of rupture speed is termed as the super shear rupture speed. The rupture speed to the north is less well determined, but its speed is probably between 2.5 to 3.5 kilometers per second. Another important evidence to constrain the rupture speed is this Nabidal strong motion station, which is indicated by the triangle on the map and in this time and space diagram. The timing of these big rupture pulse or big amplitude of the velocity waveforms clearly capture the arrival time of the rupture time, that the rupture front that went through this Nabidal station, because this Nabidal station is only 3 kilometers away from the surface rupture. It's very close to the fault. So its timing, the timing of this rupture phase is indicated, its position is 216 kilometers to the south of the epicenter. Its timing is about 46 seconds after the origin time. So it matches with the back projection and the multiple point source inversions results pretty nicely. So that is an independent observations that support the southern part of the rupture is super shear. When we put all these observations together, the regional and local strong motion waveforms, teleseismic observations, as well as geodetic deformation, which is the 3D surface deformation derived from the images that I shown earlier. We produce this kind of snapshot to indicate at different timing how the rupture evolved along different segments of the fault. So the total duration of the earthquake is a little bit more than 1 minute, and multiple observations from back projections, from multiple point source inversions, as well as from finite fault inversions matches each other. So again, this is to support that this earthquake started with a sub-shear rupture speed, which is have a rupture speed about 3 kilometers per second. As it propagates to about 100 kilometers to the south of the epicenter, its rupture speed becomes more than 5 kilometers per second, which is a super shear. And this is the data, which is shown in black, and the synthetics shown in red. The comparison between the teleseismic body waves and the synthetics. So this finite fault model you've seen in the previous slide matches these observations pretty nicely. It's another support to the robustness of this finite fault. Not only these teleseismic body waves, but also these Nabidal strong motion stations can be matched well with this finite fault model. So this black indicates the 3 component up and down, north, south, and east, west observations recorded by the strong motion station, and the red indicates the synthetics or model predictions from the preferred finite fault model. The water component is less well fitted because it has smaller amplitude, probably subject to stronger 3D velocity structure impact. The other 2 horizontal components are match well by our preferred model. And this is the, the match to the geodetic observation. Now the geodetic data, which is shown in the lower 3 panels, north, south, east, west, and up and down components, these are downsample 3D surface deformation compared with what you have seen earlier. And the middle 3 panels shows the model predictions, again shown as north-south component, east-west, and up and down. And the top 3 panels shows the mismatch between the data and the model predictions. Again, the finite fault model matches these geodetic observations pretty nicely. So these multiple data sets provides a more robust constraint to its spatial and temporal evolution of the rupture on the fault. There are actually additional evidence that we can extract it from the near fault strong motion data station Nabidal to provide actually further constraints. This is a little bit complicated, but let me try to explain to you. What you are seeing here is the fault parallel, which is shown in blue, velocity waveforms, and the fault normal, which is, blue is fault normal, and red is fault parallel components from the Navy Dal station, which is located less than 3 kilometers away from the surface rupture trace. And we can measure the fault parallel component amplitude and fault normal component amplitude. These are representing the rupture pulse that are passing through these Navy Dal station. And we can compare the amplitude ratio between the two. And based on numerical simulations as well as lab experiments, the amplitude ratio between fault parallel and fault normal component is an indication of the rupture speed that is passing through this Navy Dal station. So this ratio is about 1.2, and its corresponding rupture speed is 1.5 times of the shear wave speed. So that is more or less about 5.5 kilometers per second, given a shear wave speed of 3.3 to 3.5 kilometers per second within the upper crust. So this amplitude ratio between different two components of the Navy Dal stations also requires that the rupture speed that propagating through the Navy Dal station has to be faster than the shear wave speed. Next, I'm going to show you more near field observations from this earthquake. This is a co-seismic damage zone width constrained by the optical images. What you're seeing in the panel A, which is in the middle of the diagram, is a it's a high resolution north-south component or fault parallel component across the fault. So red and the blue are going to the opposites. So when it's blue, it means that it moves to the north, and when it's red, it means it's moving to the it's opposite. Blue means it moves to the south, and red means it moves to the north. And by drawing cross sections, for example, this is a cross section profile number 1, that what you are seeing here. We can see, that these numbers are not shown at the bottom, but I can tell you that this is a very sharp offset across the fault. With these 10-meter spatial resolution optical images, we can measure the so-called deformation zone width to be about 60 meters. In contrast with this very sharp co-seismic deformation zone across the fault, this profile number 3 shows a much broader zone, as you can tell from this cross fault parallel component to the across the fault. And this transition is much gradual compared with this profile, and this damage zone width is about 300 meters. So if we scan this entire 470 kilometers rupture for every 500 meters, we can extract the co-seismic damage zone across the entire rupture. So these bars across the fault is indicating the width of this co-seismic damage zone, and they were color-coded by the co-seismic slip amplitude, which is consistent with what we shown in these slip models. As you can see, these co-seismic damage zones show pretty dramatic differences across different parts of the fault. They could be caused by very different reasons. For the interest of time, I won't going to explain these co-seismic damage zone width variation to greater detail. What I'm showing you here is kind of is a continuation of what I said from the very beginning. So I told you that we have deployed multiple strong motion and broadband stations along the fault, and each of these triangle is representing a strong motion and broadband co-located broadband stations along this seismic gap. And what you are seeing in the map wheel here, these are the two components. So what you are seeing to the left is the black is the vertical component of a teleseismic event, the waveforms, and the red is the radial component of a teleseismic event waveform. And this event is coming from the eastern side of the fault, as shown in this blue dot in the inset panel. And this is the station, which is the station number, station more or less showing the center of this rins. So 30 means 30 degree in epicenter distance, 60 degree. So the earthquake is located at a teleseismic distance. So the P wave comes in a near vertical direction. So this is in a interesting contrast for an earthquake that is located to the western side of the fault. So this is the other vertical and radial component waveform record by these stations. They plotted together. So if the event comes from the western side of the fault, you can see a clear delay between the radial component and the vertical component on the recorded waveform, right? So this is a very strong contrast. So what is the reason that causes this delayed radial component arrival time relative to the vertical component? We have tried many models, and the most possible model is that there is a fault zone that is dipping to the west, so that when the event comes from the west, the incoming ray passes more or less parallel with the fault zone boundary. So this multipassing effect across the fault zone, which has within the fault zone, it has pretty low shear wave speed compared with its confining rocks, so that this radial component arrives 1 to 2 seconds, more than 0.5 seconds later. So the top figure is showing the statistics of these 3 represented stations, M02, 06, and M11 stations. And each of the square is representing the delay time between the radial component and the vertical component. So this phenomenon is not only persist for these representative 2 events, but with a almost complete azimuthal coverage, we can see a clear contrast between the events coming from the east, which are back azimuths from 0 to 180 degree, than those coming from the west, which is 180 to 360 degree. So this is a requirement to have a west dipping fault rather than the east dipping fault. So this is the receiver function waveform for M02 station. So based on this waveform, the derived receiver function waveforms shows a negative pulse for the very beginning part of the waveform at a 0 time. So this requires a delayed radial components. So by modeling these receiver function waveforms, we were able to match the observations, which are shown again in black, and the synthetics in red. So for this M02 station, we use west dipping fault. So its dip angle is 80 degree. The width of the fault zone is 2 kilometers, and the velocity reduction within the fault zone is 45%, which is pretty dramatic velocity reduction within the fault zone. So this fault zone was formed by multiple historical events, and probably like some of them would like these 2025 events, because the rupture process of the earthquake produced damages to the rocks, and accumulation of multiple earthquakes or ruptures would be able to create such a fault zone that is characterized with very low velocity compared with its confining rocks. So these are the research results that we use to constrain this dipping fault geometry and its velocity reduction. So this kind of fault zone or velocity reduction around an active fault is not new. Based on seismological observations, many other investigations, which are indicated by other squares rather than this red square we have here. This is shown as the width of the fault zone as well as the velocity reduction in percentage within the fault zone. So many of these faults are located in California. Some of them are along the Alpine faults, and some of them are in Turkey. To constrain this kind of fault zone, the other studies use this very dense seismic array going across the fault, but with the broadband stations installed almost exactly on the fault. We were also able to use receiver function techniques to constrain its width, which is pretty wide compared with many other fault zones, and its velocity reduction. So paleoseismologists have already mapped this Sagan fault. The figure to the left was mapped by Dr. Wang Yu, who was this work was done when he was a PhD student at Caltech. As you can see, the surface fault traces are mapped by geologists are more complicated than those produced by this recent earthquake. This recent event produced a very simple, very straight, very long, almost no stepovers or branches along its rupture. But earthquake geologists map a bit more complicated fault traces. So an implication is that these secondary fault branches probably were produced by the smaller historical events, and this very wide fault zone, in the middle of this very wide fault zone is the rupture of the 2025 earthquake. This accumulation of past events probably created a very narrow and very weak, even weaker than those other parts of the fault zone. It's like a superhighway for rupture, so that this rupture can propagate with the minimum amount of resistance and allow its propagation to be more than 470 kilometers. So this is our conceptual interpretation for the co-seismic rupture for the 2025 event, and the other secondary faults were mapped by the geologist. Finally, this is my last slide. I would like to explain this supershare transition as shown in the finite fault model as well as the back projection. It takes about 100 kilometers for the rupture speed to accelerate it to supershare speed. And this could be explained by a theoretical calculation, which is this LC parameter. And based on dynamic or earthquake simulation, which is shown to the right, that if these taus, this number of relatively, this is so-called relatively stress drop parameter, is very small, which is the case for this earthquake, the fault rupture length, the transition rupture length has to be about 100 to 200 times of these critical lengths of the fault zone. So this dynamic rupture model can explain the transition of the supershare rupture, which has taken place about 100 kilometers to the south of the recent earthquake, of its epicenter. But the fault geometry variation might be playing a role as well, which was shown in the static slip model, that the fault dip direction changed from east dipping to the west dipping, almost also at the distance that is about 100 kilometers to the south of the epicenter. There are also dynamic simulation shows that when you have a geometric geometry change, in particular this kind of anti-dipping fault geometry change, that supershare rupture can also be promoted. So finally, this is my take-home message. So this earthquake produced a 480 kilometers long surface rupture. The subshare rupture speed transitioned to supershare, which is about 5.3 to 5.5 kilometers at about 100 kilometers to the south of the epicenter, and sustained this rupture speed for at least 200 kilometers. And using these near fault observations, we can also constrain the supershare rupture segment has a 2 kilometers thick low velocity fault zone structure. And then this kind of fault zone structure can explain the supershare transition, which means that the distance from the epicenter to the place that the rupture speed is passing the shear wave speed. And thank you for your attention. I would like to take any question that you have.
Thank you very much, Ch1, for your talk, for introduction to the historic seismicity in the region, observational network, the nature of the rupture process, and the indications of its supershear characteristics. Are there any questions from the audience?
Yes, Monica, there are, but we are slightly running over time, so only one quick question for Ch1, and that is, if you could please elaborate on how you define the seismic gap in the study region, if it is only defined by the lack of major recent seismicity in seismological and piloseismological data, Or do you also use geodetic measurements to show a high coupling in the potential seismic gap?
The seismic gap here is defined from historical earthquakes, mostly. As you can see from this map, there are other events that happen in the past were indicated by these blue dots or gray dots. So this is a segment that has about 200 years of silence based on the paleoseismology observations. Geodetic observations cannot resolve whether it's a seismic gap or not, because quickly, say a few years after the earthquake, a big earthquake, the fault locking status will be recovered to the status that is before the earthquake. So what we have from GPS is a bit doesn't have any sensitivity to the seismic gap. So not only based on seismology, paleoseismology, but also this Choir zone is also presented in the earthquake catalog that is available since 1970s, so that these two lines of evidence strongly suggested that this is a gap that earthquake studies should be paid close attention to.
Thank you very much, Ng. I think this answers the question very, very well. And thank you again for the very interesting presentation. We leave now just 1 minute offline so that we reconfigure the link for the next presentation about the Kamchatka earthquake. And that's thanks, Ng, again, for a wonderful talk.
Thank you.